What I did here is I'm going to be using slides that I had from a presentation, and then at the end I will have slides specific to the problem, to the exercises that we are going to be doing. The idea here is that you become aware of how to describe hardening using a model that is not the Boche model, but a model that is based on the evolution of dislocation density inside your material. So there are many of those models. In the code we have two or three of them that can be used. I'm going to be referring to the one in which we have the one type of dislocation that are called reversible dislocations. So what motivates this problem, or what motivated that problem, is this experiment that were done on interstitial free steel. They were done at minus 120 degrees C and 20 degrees C, so at low temperature and at room temperature. So the material was deformed by shear in the forward direction, and then it was reloaded in the reverse direction in both cases. So in both cases you see two things: that the yield stress is lower than the value unload, that there is plateau here in the stress strain curves, there's a plateau there in the stress strain curve, and then the hardening starts catching up and reaching the value that you would have if you do just a monotonic shear test. Okay? When these guys looked at the microstructure, what they see is that the microstructure that they had tends to be erased, going from this is the microstructure after 30% forward shear, which are these values, and then they did the experiment, but these microstructures only show 5% reverse. What they start seeing is that the dislocation structure starts disappearing if you reverse the sense of shear. So the TM shows this dissolution of the dislocation structure. So when I started working with them, the idea was, okay, how can we introduce that into the models? Well, people have looked at what is called the kinematic hardening model, which is a rather empirical way of dealing with the effect of reversals. And the kinematic hardening model is based on the idea that if you have a yield surface like the red one here, and you deform your material, your yield surface is going to translate in the stress space and become the green yield surface. Okay, that is why they call it kinematic hardening. They displace rigidly the yield surface. So this is the stress acting at this point. So when you reverse the shear, then you go through zero, and the reversal finds the yield surface much closer to the origin. So you have a lowering of the yield stress. So you are here. This point is there, and this point corresponds to the yield at this position. So they say, okay, with this we solve our problem of reversal effect, the stress differential. It is not so good because this is limited to exact reversals, tension compression or shear reverse shear. And there are some empirical parameters that describe the translation of the yield surface, but the physics is really lacking in doing it this way. Yes, you get what you want to get, but the physics is not in the problem. And of course, if you do shear strain path changes that are not reversals, so you do tension followed by shear, or compression doing by compression in other direction, anything that you can think about, then this type of kinematic model really is very difficult to implement. So, as I said, people have been dealing with this issue of strain path changes for some time, and I have listed here a few papers that deal with that. I'm not going to go into this, just to tell you that people have been worried about this, but there is an important aspect from the point of view of modeling. You're going to get these slides later today. There is an important point from the modeling perspective. That is that most models adjust parameters to monotonic tests, tension or compression, to monotonic tests. But when you change the strain path, and then you can, especially dislocation models, there are tens of dislocation models, and you can fit any of them to any set of monotonic curves. But then if you say, okay, does this model work if I stop my test and I start testing my material in other direction? Then most models just break down, because it is easy to adjust things for monotonic, but you need to capture what is going on when you reverse the sense of loading, reverse or change the sense of loading. And so that is the real test of a plastic model. Can it handle changes in strain path? So in 2007 we started thinking about this problem, although we were not the first ones, of course. This is not the first time. We came up with one model that was the basis for what I'm going to be describing in the next slide. This model, of course, has a certain total amount of shear. The gamma dot is the gamma dot given by the power law, and but what is important is the way we treat the tau critical. So the tau critical has three components here. The first component is a threshold stress that has to do just with the dislocation structure, just how the dislocations are tangled in your system. The second component has to do with that is called delta tau cut. It has to do with the extra stress that these dislocations need in order to cut through the previous forest that you created in your material. So usually when you deform, you create a cell structure. You change your strain path, and that cell structure gets replaced by another cell structure. But in the process, you have to destroy the cell structure that you created first and create a new cell structure. So for that you need an extra amount of stress, which is this delta tau cut here. And then there is the delta tau rev, which is when you deform your material, you create some reversible dislocations that are kind of held in place but can be easily reversed if you change the sense of shear on the slip plane. So we propose a model that has those three components. They were treated in a rather empirical way. I'm not going to deal a lot with that particular model, but let's say that this one was treated using just a simple Voce law, that this is the one that we have been seeing. This one is treated as an exponential that has a term here that V nu, which is has to do with the creation of new structure, and this one has to do with the presence of the reversible dislocation. So this has to do with the microstructure annihilation part. Anyway, we apply that model to copper, and these experiments are 8% tension followed by compression, which is this one. So this is monotonic tension, and this is 8% tension followed by compression. This one is 18% compression followed by tension, and 28% compression followed by tension. The experiments are not our experiments; they were done by other people. But the fit to the experiments, which is also here, is very good using that model. We also did some experiments on copper doing the channel die process that we showed before. That leaves your material with a dislocation structure that is characteristic of that process. And then what we did was we did 20% compression on those samples, cutting samples in three directions, because now we have a square parallelepipedic sample. We cut cubes, and we tested the cubes in the three different directions, and sure enough we get very different results depending how we are compressing with respect to the previous shear direction that we introduced during equal channel angular extrusion. And once again, here are the results of the experiments and the results of that we obtained with that model. So years later, I started collaborating with these people in the University of Aveiro, and then that is when we started discussing doing this more from the point of view of the evolution of dislocations in individual systems, which is what I'm going to be showing today. So this was the last paper that we published, but we published a couple of previous papers having to do with that. So the model is based on an assumption, and the assumption is that when you create dislocations, you create dislocations that are going to become a forest and that are going to be locked in place, and dislocations that can be easily reversed. So the model has each system has dislocations that belong to that forest, and then reversible dislocations that are easily reversed in the positive direction, and dislocations that can be reversed in the negative direction. So the positive and negative means that the shear took place in the positive sense of the Burger vector or in the negative sense of the Burger vector. Then the threshold stress is given by a Taylor law, where there are some hardening coupling parameters. The tau is the square root of this sum of hardening parameters times the dislocations in each system. And this law is usually used in this simple form. That is the Taylor law, where you say the critical stress is a certain initial threshold and something that increases with the square root of the dislocation density. S and S prime? Yes, prime. Yes. This is the critical resorption stress to move dislocations in the system S. So if there are dislocations in the system S prime, so in any other system, those dislocations are going to oppose. So if there is no dislocation in any other system, you only glide on one system, then you have this parameter, alpha SS. So it's the dislocation gliding in the C system that maybe they are going to start cross-slipping, but they usually don't put so much of an obstacle as dislocations that are perpendicular to the dislocation that wants to propagate. And so that's why these parameters are different, and for the cubics this is not really so necessary. In hexagonal materials, yes, it is sometimes important to make sure that the basal dislocations interact differently with other basal dislocations than with, say, pyramidal dislocations or prismatic dislocations. So not all the dislocation densities are the same. It depends on in which system they are happening. No? So the model says the following. Forget about this for a moment. Let's look at this, which is the classic Cox-Making hardening law. It says that the change in dislocation density total is a certain generation parameter K1 times the square root of rho minus an annihilation parameter that goes with the dislocation density already present in your material, and then times d gamma, which is the total amount of shear. So we decided to split that law in two. So d rho total, if d gamma is positive, which here positive or negative is arbitrary. We say this Burger vector is positive, this is negative. We decided that when d gamma is larger than 0, then we are going to form forest dislocations and reversible dislocations. And so we write this law for both of them. But here there is only the forest, here is only the reversible, and we add a parameter which is a fraction of reversible dislocation generated. So as you produce dislocation, you are going to say what fraction of these dislocations will be reversible and which fractions are going to tangle and become immobile, let's say. And so that parameter P is 1 minus P. At the beginning, P is 1, which means that all the dislocations will be reversible. And as the formation proceeds, the reversibility is going to decrease and decrease and decrease. It's going to go to 0. If you add these two things, you get the Cox-Making law. So for monotonic loading, this model doesn't really help you much. For monotonic loading, it doesn't really help you much because the sum of these two things gives you the Cox-Making law. Now, if you already had dislocations, reversible dislocations in that system coming from a previous process now, that is why there is also these dislocations, they are also going to change when you put a shear in the positive sense, you are going to get a change of the reversible dislocations that are in the other sense. In a way, what this term is doing is saying, if I want to accommodate shear in this direction, but I already have dislocations that were generated by shear in that direction, then I'm going to recombine them. So I'm going to use them up. And that is kind of proportional to I'm not going to go in details of why it has this form, but this term has to do with how many reversible dislocations are in that system. if I don't have reversible dislocation in that system, it is not going to contribute anything. But if not, this dislocation was generated during a previous process, then when I reverse, they get used up. Concerning the P parameter, we propose that a simple evolution. We propose that P decreases as the dislocation density increases, and this is a sigmoidal. We propose a sigmoidal curve, and we adjusted these parameters, the initial point and the final point of the sigmoidal. We adjusted that within a range of deformation. D has to do with the accumulated dislocation. However, as you can see here, D only increases if the dislocations are non-coplanar. So if the dislocations are not in the same plane, but if the dislocations are tangling. If the dislocations are in the same plane, we say that those dislocations will be overall all reversible, and so we don't count them. So what happens is that then, if you have a monotonic loading, yes, the reversibility will decrease. But if there are reversals, the reversibility can increase again. So you can clean your material of dislocations and create more reversibles as you go by. So there are two consequences of doing this model, and the two consequences are that one is the Bauschinger effect. So now what each system sees, and this is programmed in the code, this formulation, it sees a critical stress that is an effective critical stress, which is the tau intrinsic, and a delta tau that has to do with the fields of those pileups of dislocations that are there waiting for you to reverse and are going to help you to move dislocations more easily. So this delta tau has to do with the number of reversible dislocations, and is what will give you this Bauschinger effect. As you can see, it has a minus sign there. But the other thing is that as you keep deforming, you keep using up your reversible dislocations, and so your critical stress does not increase, because your total dislocation density remains the same, because you are using up reversible dislocations. And so this term that I showed before is responsible for giving you this plateau in the loading curve. Eventually, you run up of reversible dislocations, and then this curve will go up again and join here. So that is essentially the tau threshold that we are going to put in our law. I showed this slide before. The tau threshold that is going to go into our law is the tau intrinsic plus a correction to it because of the presence of reversible dislocation. So shear rate on slip systems, stress and strain rate vary from grain to grain, history of the formation, and so dislocation densities are going to be different from grain to grain. So now every grain, depending on its orientation, is going to have a different dislocation density, and this is going to be evolving with the dislocation evolution. So we apply this model to low carbon steel for two problems. We did tension on big samples, and we did tensions on big samples, and then we cut from those samples shear samples. These smaller ones, these are shear samples. They have a groove in the middle, and so you do shear like that, as the arrows indicate, shear like that or shear like that. Now this is the initial texture of the material. This is a body center cubic material. And these are the stress strain curves of the material in tension, and then it was followed by shear at 45, 90, and 135 degrees. These three types of tests. So there is a change in strain path, which is tension followed by shear at different angles. So these are the results when you do 10% tension preloading, and then you do each of these shear tests. These are the shear stresses that you get. And what you can see here is the 90 degree, which is this one, which is cross shear. It really goes against across the previous dislocation structure that you created, is the one that has the highest flow. And the green one, which has the lowest one, is the one that corresponds is the closer to doing tension in this direction. So this shear stays here on this sample is more or less equivalent to doing tension. If you compose the arrows, it gives you tension in that direction and in that direction. Okay, so that is you continue to do the same. And the red one, which is at 45 degrees, if you do 20% preloading, and then you reload, you get similar results, a bit more of yield stress because now you deform more in tension. But as you can see, the model that I just presented, which are the full lines, reproduce very well the experimental points. They go through the experimental points fairly well. So the model is sound in that respect. So there is in the distribution code, there are two cases, which is the tension followed by shear at 90 degrees and the tension followed by shear at 135 degrees. They are in those folders that are indicated there. I will leave that up to you to reproduce those results. Okay? Yes, the simulation include the preloading. Yeah, because you need to create that dislocation structure with reversible and forest dislocations, and then load that in shear in different directions. So the simulation includes that process. Yeah, include that process, the rotation of the sample, etc. But I wanted to do another case and present that as an exercise, which is this one. On the same steel, actually, it's a slightly different composition. You're going to see that in the folders there is a low carbon 1 and low carbon 2. So these are two slightly different compositions of steel. So they give you slightly different stress strain curves, and we adjusted parameters for both of them. So we provide the parameters for both of them in the code. But today I wanted to do the exercise with the cyclic shear, because I also think that this is a neat result for many reasons. So what you see here is experiments done in shear up to 10%, 20%, 30%, and 40%. So this is shear up to 10%, you reverse the shear minus 10%, you load again 10%, reverse 10%, 20%, load another 20%, and finally unload, okay? You do the same with this one, you come here to 20%, then unload, you get this red curve, the top one, you come here, you reverse again, you get the bottom one. Now, one interesting thing, and then you do the same with 40%. Now, one interesting thing here is that you get a saturation. In each cycle, as you can see, it doesn't take much long to saturate. It's not that each cycle will show that there is sustained hardening. It's not that you do this. You're not doing that. In reality, in actuality, what this is doing is doing this. Maybe, and it is staying essentially on the same curve. So this is something that I told you that we had three versions, 3 papers published with this model. But we didn't have this in the previous 2 models. But then when we started looking at the shear results, we realized that we needed a mechanism which is we had to exclude the coplanar slip from hardening the material, from contributing to the reversibility parameter. So on the contrary, they had to the reversibility parameter was not changed if we have coplanar slip, and that is because in shear you don't activate a lot of systems. You activate 2 or 3 systems per grain, and you can check that when you do your simulation. You look at the activity file, and you will see that the activity per grain is not 5 systems certainly. So you are mostly dealing with 2 or 3 systems per grain that are active. So those systems just keep going back and forth and recombining, and do not create too much dislocation structure, as opposed to doing tension or compression, where you do create that dislocation structure because you activate more systems. They are not all coplanar.
Yeah, if slip is mostly coplanar,
slips as mostly coplanar, yes.
Yeah, then when you reverse, is it just easy for them to kind of run back out and you kind of clean up your system?
Correct. Then your dislocation density is not going to be increasing much because you generate them and then you recombine them. You generate them and then you recombine them. So that is what is happening, and that is when we had to revise the reversibility parameter in order to capture that effect. So that is of the three papers that I listed at the beginning. That is what we include in the third one. There is an application for magnesium also, but we are not going to touch on it. But we also apply this to magnesium. When you reload, it kind of shows softening and then hardening. Okay, yeah, this has to do because here you are using up more more of your reversible dislocations, and then the reversibility parameter increases. So you increase your reversibility, and it also has to do with the delta tau then that has to do with the amount of raw reversible dislocations. As you annihilate your raw reversible dislocations and generate less forest dislocations, overall your dislocation density, the total dislocation density, decreases, and then your flow stress is also decreases. Now, in those curves, what I have done is, if this is the load part and this is the reload, this part this part from here on, it was put there. So essentially, that is what. Then you have this. You unload, and then you have this part. This part was put there. So those curves that you see there are the same for 10%, 20%, 30 or 40%. Are the same as those curves, but kind of made positive. All the shears were put in a positive scale and in a sequential. But they're the same result as this one, and it makes it also easier to compare the experiment and the predictions. The experiments are the dots, and the predictions are the full line. We don't have elasticity in the code, so that is why these curves do not start from zero, because we never start from zero with this code. We start from some yield stress, but we don't have elasticity. So the elastic part of the curve, whatever is the elastic part of the curve, is missed by this model. As a matter of fact, the comparison with the experiment was done subtracting the elastic component. So this is what is happening now with the dislocation densities. You can also follow the dislocation densities. There is an output file called dislocation density .out. This then .out. And you can follow that. What is happening is the reversible dislocations are really the ones that are most active in this test. And as you can see, they increase, and but essentially after this point, the first reversal, they essentially keep doing the same thing. You don't increase your dislocation densities. The forest tends to increase here, but the reversible ones are the largest portion, and they just keep oscillating there. So you pretty much keep your dislocation densities constant. Observe that where the reversible dislocations have a minimum, the forest dislocation have a maximum there. No? So this is the exercise that I would like you to do. This is shear and reverse followed by reverse shear. So only two strokes, shear and reverse shear. You can do the cycling if you want. You just put more processes in the simulation, and you will get those curves. But it's just the first two strokes. So the files that you are going to be using they are here in this directory. LC steel shear to 30%. There is the texture of the steel. There is the single crystal file for the steel. This problem was run with n effective equal 10, so something in between the tangent and the secant. And as I said, there is a process file that has 30% shear and followed by minus 60% shear. Now, this is, I think, the first application where you are going to use more than one slip mode. So far, we have been doing FCC. This is a BCC material, and the BCC has three sleep systems, three sleep modes, but one can do with two really. So they are listed. They are listed in the single crystal file. There are three modes. We are going to use two, which are the modes 1 and 2. One is the 110 111 sleep. The other is the 112 111 sleep. This 123 111 sleep doesn't make a lot of a difference, and so I didn't include that one. You are welcome to say, okay, I want to deform the material with the three modes, and just you will be including that one. This is the second part of the single crystal file. The second part of the single crystal file gives the parameters of the model. And as you can see, this is for the steel one, that is the one that we use for the shear, reverse shear. This is for the steel 2 that we use for the tension followed by shear. So as you can see, there are more parameters than in the case of the Boche law, and well, you can take a look at them, but it's not. They are the parameters that appear in the law. I don't want to go too much in detail. The powers that appear in the back stress law, this parameter that also appear for the reversible dislocations. Unfortunately, this example is one of the examples described in our book. You are not going to find it in that older version of the code, that the VPSC that I distributed the manual. In that manual, this example is not going to be present because the VPSC7C is an older version, and at that time we didn't have that this implemented. So and as I said, it is in the book, but the book is not yet out. So you will have to kind of believe that these are the right parameters. You can, if you are really interested, you can go into the papers and look at in the papers what the description of the model and each of these parameters in the law. So, but these parameters, as I say, are in the single crystal file. And then the conditions for running are: we are enforcing all the velocity gradient components. We are doing 300 steps of 0.1%, and we are enforcing the component 6. The component 6 is epsilon L12. So 300 steps of plus 0.001, and 600 steps for the reversal, 600 steps for the at minus 0.001, okay, with increments of 0.1%. And this is the textures that result. We start from a material that is initially textured. This is the actual experimental texture of the material. After the first 30%, you get a shear texture. For BCC, this is different from the look of the texture for FCC. Although if I would plot this is slightly different because you have now two modes of deformation, not one mode of deformation. If you only had one mode of deformation and you plot the 111 poles, the 100 poles, they will be similar to the 111 poles. Usually that's what happened because the Burgers vector and the normal to the slip systems are reversed when you go from FCC to BCC. There's a symmetry when you deform them, and so when you plot 111 poles, they give you something. They give you the same texture as when you plot 110 poles for the BCC. Anyway, texture at 30%, then you go through 0. When you go through 0, observe that we practically recover the initial texture. We have fully reversed the shear. So we recover the initial texture here. And then we go a further negative 30%, and this is what the texture looks like, which is similar to this one, but with a rotation. So the files that you may want to look at and plot are, well, this is the stress strain. This is the stress strain curve, which is load and then reload. And as you can see, you were talking about the dip. The dip is there. If it is not a full dip, it is a nearly a dip, but it is very clear that there is something going on here with softening. And then there is a file, this then.out, that as a function of the formation, and this is the component 1, 2, but this is the von Mises strain. This is the von Mises strain. This is the control strain. So this is the 1, 2. You have the average raw forest, average raw reverse, and this is the raw total, which is the sum of these two lines. And then you have how many dislocations are contributed by the mode 1, that is the 110, 111, and by the mode 2, that is the 110, 112. So this is a contribution of each mode to the formation, and these are the total of the forest and the total of the rivers, and those are plot here. So with that you can now go into this directory, copy the file MEMS-IIT into the root directory, and you can run this problem and plot those textures, dislocation densities, and stress strain response.